So this will be like a tutorial style talk, I think. So not like a 1 hour overview and 1 hour in depth, but more like a 2 hour straight tutorial. Is that right?
Actually, it's more or less an hour, and it's more or less an overview over the field rather. Right? I will not go that much into depth.
Okay. So a 1 hour plus overview, and then everybody's highly encouraged to make it even longer with whatever questions we can find. For people who are panelists, they can just unmute and speak. You can also ask questions in the chat, and I'll try to have the chat monitored. Anyone who's watching this over...
an overview over the field rather. I will not go that.
Anyone who's watching this over the YouTube channel, please try to join at the Simon's Zoom meeting instead if you want to ask questions. Attendees, I think, cannot speak. They can just join. They can send chat messages. If you are an attendee and want to become a panelist so that you can speak, just send a message and we'll take care of that. Today we have one of these clearly beyond SAT topics. We're going to learn about answer set programming, what it is, by arguably one of the experts or the experts in the field, Torsten Schaub. So who is his behind CLASP, which is I think one of the best known answer set programming solvers, and lots of this is a tool that can do lots of other things also, like SAT solving and pseudo Boolean solving and what have you. So we won't spend a lot of time on introducing you or your wonderful CV. We just want to hear you talk. So please, without further ado, please.
Okay, first of all, thank you very much for the introduction, and of course also for the invitation. So as I mentioned at the beginning, unfortunately my Linux box wanted me to log into with a Berkeley account. That didn't work out. So I'm now back on my iPad and have to improvise a little bit. So can you see my mouse highlight like this?
Yes.
That's good, very good. Okay, so actually I decided to, I have a tutorial material on this, and actually we have our course on ASP online. So if you really want to know more about ASP, I can give you the URL again, but it should be easy to find. So I decided to rather concentrate on an overview over it and be rather shallow. So some of you may actually ask, oh, this is so shallow. Well, in this way, I can cover more ground. That was more or less my motivation for doing that. Good. So here is the outline. So I'll start by motivating the whole thing. Then I give you a very crisp overview what ASP is. Then highlight actually the history of it, because I think this is interesting, in particular for those of you who have a SAT background. And well, actually, if you want, propositional logic goes back in its current semantics to bool or whatever. These foundations were not available for ASP and formalisms alike. So it's interesting to look where we came from. Then briefly look at foundation, and then actually see how ASP can be used. And then I will also highlight in chapter 6 a couple of topics that I will not talk about, which I find really interesting. And then just recap. I have actually some additional material on the logical foundations, because I think this is interesting also from a general point of view, because you can always ask the question, I'm doing classical logic, propositional logic, first order logic. How can I make this non-monotone to implement closed world reasoning? And actually this is then the logic that will do this for you, which was actually just discovered in the 90s, right? So that's actually quite interesting, even though it traces back to logic foundations well beyond. Anyway, I don't want to deviate too much. Anyway, there is some additional material here. In case I forget to mention, bug me in the question series. Good. So motivation, first of all. So I think in SAT one can say, well, the big breakthrough of SAT was its applicability to computer-aided verification. And I think from my perspective, and you may have another perspective on this, this had, of course, quite an effect on the development of satisfiability solving. For instance, that in the area one mainly focuses on solving, And there's not really a modeling methodology or even a systematic approach to variable instantiation, just in the same way as there is a clear interface to SAT solvers with Dimex up front, and then perhaps then some format for the output. But the other things are missing. Why that? Well, my belief is that in hardware verification, you normally have modeling languages and you just wanted to compile things down. So this didn't pop up. But this is different here with ASP, because ASP grew out or is situated in knowledge representation and reasoning. And they are modeling, having a knowledge representation language, modeling at a high level is very important. And let me just go through this a little bit, even though I think this is basically all pretty obvious. So with traditional software, and now I'm talking about any type of software, we have a user, and this user wants to solve a problem. So more or less the program does problem solving, and this is then mapped on a computer. So what we have as a role here is that of a programmer, and this programmer actually with a program, the programmer describes a path to a solution. So in German, we have this nice word, we can always compound words, Lösungsweg. So the path to the solution. This is actually what the program does. So you read it in, do this, if this, until something happens or whatever. This is what happens here. So the idea then on the other side, sorry, I'm too quick here. And then what this program describes, it's an answer to the how question, how to solve my problem. And of course, the dream in AI is to go beyond that. And I now like to term this knowledge-driven software, where the idea is you declare your problem, but you leave actually the solution to the computer. This is a very old dream, of course, which goes back, I think, to the beginnings of AI. But I think now with solver technology, we can realize it. This is more or less what ASP tries to do. Okay, so what we have, rather than having a program here, a monolithic program, we have two components. We have a general purpose solver, which is just like a computer, just that it can, in the sense that it can address a certain subclass of problems. And then actually here, the actual problem is just specified more or less by dumping the problem knowledge. And I think as many of you know, actually the scale here is not really appropriate, because of course the solver has many more lines of code than normally the problem specification has. Okay, so while of course the program addressed the how question, here actually we want to address here the what question, what actually is the problem, and then solve the how question, but in a generic way. That's actually why I put here an exclamation mark, in the same way as a computer who knows how to run a program, how to execute it. The solver knows how to solve combinatorial search problems. And the only the problem-specific part is this here with a question mark, which is much smaller than here in the program. So this about the situation and the motivation. So, and also of course then roles shift. While here we have still a programmer, here we have, in the best case, an expert who's not even a computer scientist. So who more or less expresses his knowledge in a modeling language, and then this is given to a solver and passed on to the machine. So what's the benefit of this? Well, first of all, an expert must only express their knowledge. That's one thing. And what you then get is, since it's really at a high level of expressiveness, the description of the code is very transparent. You can easily modify it, maintain it, and of course reliability is also something, because if you only have to verify, let's say, a half a page of logical specification, this is much easier done, of course, than verifying imperative code. Okay, this is more or less, these are the benefits of this upper part here, but actually we still dream of going higher, in the sense that we do not actually let the expert express their knowledge in terms of logical specifications, but even to go up to natural language, and then actually not only have experts but laypersons. And this is, I think, is really something, and we are not yet they are somehow in a production way, but the people are doing research on that. They're not using plain natural language, but actually controlled natural language, where, for instance, if you want to come up with a shift planning system for a larger company, then you can translate this into basic text, and the union then could vote on that, even alternative formulations on that. And this is actually one of the visions actually that the community has, and that we really try to push it up and up and up. But again, this having laypersons writing things in natural language is doable in academia, but is not yet there for a broader audience. Then, of course, for the solver, these are the same. Here we find the same advantages that we have with SAT or CP solvers, right? They are general, they are effective, they can prove optimality in the sense they are complete, right? And they are freely available. That's more or less the same thing as you have also in other communities. Okay, so this is more or less the picture then we are faced with. And again, what is really different here is that things are driven from this idea of doing knowledge representation and reasoning. And this, of course, has leads in ASP to certain design decisions which are different than in for instance, in SAT or even in CP. Okay, now I talked a lot about it. Yes, please.
I don't know if it will get us sidetracked, but I just thought if we're going all the way to natural language, are we sure that the user even knows, I mean, has like a fully consistent specification in mind? I mean, it might be that they have maybe design goals that are mutually inconsistent because they wish for something that is too good to be true. Maybe.
Yes, and this is even the case, right? So let me. So again, I'm not talking now about really an application that started with natural language, but even we are doing shift planning actually for Swiss Railway, and there all the existing shift plans that we got were all inconsistent. And this is actually something that the system has to cope with to more or less identify inconsistencies. So the typical thing is simply workers are allowed to fix their holidays, and actually night shifts are very popular because they pay more. And then somehow already by fixing these, normally things get inconsistent. And then of course the poor guy who is normally doing the shift planning manually, the guy stands and says, oh, I need this vacation, or I need this night shift. What should I do? Then he, of course, bends a bit the rules and something gets inconsistent. So even on the logical specification level, we already see these inconsistencies and have to deal with it. So I'd say that pushing things up to the natural language level will not necessarily give us another quality of inconsistency. But of course, it will also be there. The thing I should also say is, so at least the person who we are collaborating with is Rolf Schwitter. He's working at Macquarie University in Sydney, and he's using controlled natural language, right? So the idea is not that you write free text. It's a bit the idea when you write an SMS on your cell phone, right? And you would only use completion. So you could not actually freely type text, but you could only more or less use the vocabulary that the editor provides to you. And this, of course, helps a little bit in keeping inconsistencies low. So, that's a bit the thing with web talks, right? So, was my answer okay?
That was great. Yes, perfect. Thank you so much.
Okay, good. Okay, now let's look a little bit more about what ASP is about. And what it is, as I said, ASP is thought of as an approach for declarative problem solving. And I'm really using now the term problem solving here, because I think, again, this having this word programming in here is really a misnomer. Because at least for me, programming is something where you exercise control. And the idea, of course, here is that you only pose your problem and there's no control involved. You completely decouple your specification from the execution, right? And that's actually why programming is more or less just an historic thing, and it's a bit unfortunate. Good. So this is what ASP is about, and where does it come from? Well, one could say ASP has four mothers. So I think the very basic form of ASP is databases, deductive databases. Then, of course, where really the stable model semantics and all came from is logic programming, where people looked at the declarative semantics for Prolog, semantics for logic programs that is independent of an execution model. Then, of course, knowledge representation and reasoning, and here in particular, not general reasoning, but in particular non-monotonic reasoning. And actually, these three parents have already one thing in common. They're all non-monotonic. They all work under the closed world assumption. While in databases, this is, of course, the simplest approach where you say, well, if information is not in a database, and that thus unknown, you set it to false, this information. So you might have a default value for this. And of course, in logic programming, this was generalized because there it's not about non-membership, but there it's about non-derivability with all the difficulties that come with it. And then more or less what satisfiability solving more or less contributed is, of course, the effective solving technology. So, and I should say this really upfront, an ASP solver is not a SAT solver. It's not based on a SAT solver. So you can map ASP into propositional logic and then give it to a SAT solver, but you can also map it into MILP if you want, right? So, but actually, class, for instance, is a genuinely built ASP solver, which you can also use as a SAT solver. But more or less, I think Benjamin Kaufman, the designer, always keeps saying 10% of the source code of class more or less cover SAT functionality, right? The rest is really what you need to cover different constraints or different reasoning modes, etc., right? Okay, so this is more or less the first take-home message, that you can view ASP as a combination of database technology, notably deductive database technology, which is not only about the closed world assumption, but also the techniques that are used to instantiate a first order specification with all objects of the Herbrand universe. This is done with techniques from deductive databases, and this comes from there. Then, of course, logic programming, the syntax and the original ideas, knowledge representation, the modeling language, the reasoning modes, and SAT as more or less the parent actually that inspired the solving technology. Okay, so what is it good for? I think you all know that you can solve combinatorial optimization problems with this. But I think where really the unique selling point lies is in this knowledge intense variants of them, because you can really write nice specifications and work with them. Okay, so what problems are these? Well, this is more for perhaps not such a knowledgeable audience as you guys. So these are problems where you have a lot of decisions to be taken under constraints. And I guess here's just a couple of examples. And of course, all these examples you can just as well solve in SAT, or you can solve them in CP and so on and so forth. One thing, however, that I find interesting is, and again, I'm not talking a little bit also from our startup perspective in the company. So we get these echoes that, I don't know actually how you came up with this specification, but I think I can follow it. I think these are the rules of the problem that we have, and this is, I think, a very nice feedback actually that we get. And of course, our competitor out there in the world is not SAT, right? This is MILP, or these are systems like Cplex or Gorobi or so, right? And there, of course, you need experts who really know how to code, and more or less the manager or the guys actually or the experts, they don't really get to know, they don't get this direct reflection actually on their specification, which you get in that way. Okay, so any industrial ones here? Well, here are some highlights on ASP success stories. Actually, those of you who use Debian or Ubuntu, they may actually be using, if they don't take the standard configuration, they may actually be using Clasp and Klingo for solving their Linux package configuration. Then I think the first spectacular application of ASP was done by Michael Gelfand at Texas Tech, who used it for decision support for the space shuttle. And there are and this was the first spin-off that used ASP that was done at the Technical University of Helsinki, now Aalto University, who used it for product configuration. Okay, one thing that I find interesting, and this is not really an ASP-specific application. Actually, Clasp was used as a SAT solver. Was the frequency auction that happened in the US a couple of years back, that was run by a spin-off consulted by Kevin Leeton Brown. And what of course is interesting for us is that actually a US department takes university software off the shelf, and of course, look, this is quite a revenue that was at play at that point, and they used it, and we actually only learned about this afterwards. And what is interesting here is, so why did they use somehow an ASP solver as a SAT solver, not one of the high performance SAT solvers? Well, the history is a bit the following. So Clasp actually won, I don't know, 5, 6, 7, a couple of times the SAT competition, mainly on not in the industrial, not in the random, in the other competition, the crafted one. I don't know how it is called now. And then actually afterwards, we let it participate in the competition that was run also by Kevin, Holger Roos, and Marius Schneider, where the situation is a bit different. Where the situation is, you take your solver, and you let more or less an algorithm configurator explore the search space. And then you take the best configuration for this solver that you find for the problem, and then you compare these guys. And they're actually Clasp, at least the ones who participated, won each time, more or less. And interestingly, I think the reason for this is, of course, when we started, we didn't know actually which techniques are always good, which SAT techniques we can use, which ideas we came up with, can use or not use. So Clasp has thousands is of course exaggerated, right? But you need a pager to look at through the help menu, and it's really highly configurable. And this actually helps a lot, because if you take it as a solver and then configure it, you normally get really good configurations out of it. And this is actually how Kevin also used it here. So they had a portfolio of 2 solvers, and they built with this one solver, and there was Clasp was the complete solver, and the incomplete solver was a local search solver they built at UBC in Vancouver. So that's actually a pretty cool thing, simply because it also shows that the solvers are mature enough to be tackling such problems. Good. And well, even though I haven't really introduced ASP, what are its distinguishing features? Well, one that again we have in common with SAT solvers and to a certain extent CP, is the high performance of the solvers. But what really adds to it is this high-level versatile modeling language. And there are actually 2 things come with it. So one is the modeling as such. How do you model problems? What is a good way to do that, right? And then of course, the modeling language has first-order variables. You have to have, in the same way as you have standardized via input-output grounders, you have to, solvers, you have to have grounders that take a specification. And there is now a standard ASP language. There's a standard out since a couple of years. And then they take that guy and also then output, in the standard case, a machine-readable format similar to Dymex, just of course because it's richer, because there are also cardinality constraints, weight constraints, optimization statements and stuff like this. But that's more or less than the default workflow. And what is also built in ASP solvers right from the beginning is lexicographic multi-objective optimization. And there are tools actually that even can combine this with qualitative and quantitative optimization. So you can do, I don't know, you can form expressions that describe a preference criteria, like the Pareto of, I don't know, the minimization of the route, maximization of the fun, and so on and so on. And you can express preferences also in a symbolic way, for instance, like saying, oh, if I have fish, then I prefer white wine to red wine without ever attributing a number to these guys. So that's actually, I think, one of the nice things. And again, motivated from the heritage, from knowledge representation and reasoning. You want to have this flexibility in modeling. Okay, then, well, industrial impact, as mentioned. So we have a spin-off, Potasco Solutions, that we are running. There was even one. There was this variantum, which I mentioned before in Helsinki, and then this is the other one that is existing. It's DLV, which is running in Calabria. And yeah, so I think we are doing pretty good, because even though people always wonder a little bit, there's a logical specification and you push the button and get something out. So that's actually still a bit of a mystery. Not to mention that, and you face this too every day, that we have to explain them that we're not doing machine learning. And when you then hear the question, what is the depth of your neural network? Well, but now we get used to that. Okay, good. So that was the nutshell. Let's look a little bit at the history of it, and to get a bit of a feeling what actually the issues were in coming up with ASP as it stands right now. So again, this is a very biased view, of course, by myself, right? So so I started with looking at this actually in the 80s. Well, actually 88 or so. I think I got involved in non-monotonic reasoning, default logic, and all this type of stuff. But of course, one could trace things back, of course, to McCarthy and Hayes, the frame problem, how to do things. But well, I'm not delving into that. Anyway, in the 80s, I think there were the first attempts of really in capturing incomplete information. Then in the 90s, I think people wanted to, there was, of course, a whole zoo of different semantics around how to put them together and how to compute things. Then we had in the beginning of the millennium, we had the first application. And I think this is interesting for you guys, semantic rediscoveries. Because as I mentioned, when you look at SAT, right, all these the theoretical backbone, like, I don't know, proof complexity, semantic issues and so on, they really look back on heaps of work, on decades and centuries of mathematical and theoretical investigations. This wasn't the case here. That's actually why we were faced with such a zoo at the beginning, because there was this phenomenon, which is actually, I would say, very natural. In databases, we experience it every day, but how to capture it? It was just actually at the end of the millennium when someone proposed it, but when really the breakthrough came. Then, of course, nowadays, it's so funny. It's the same everywhere, right? It's the same where SAT started out, and at some point, theories had to be integrated. That's actually the same thing as that happened in automated theorem proving, right? There were automated theorem proving. At some point, they needed theories, and of course, the same thing also happened in ASP these days. Okay, good. Let's detail this a little bit. So in the 80s, there was the field of databases, where actually Keith Clark published this seminal paper in '78, how to capture closed world reasoning by actually viewing tables as sufficient conditions, and then actually adding the necessary conditions, more or less turning an implication into an equivalence, and to capture closed world reasoning in databases and in logic programming. And the interesting thing is, if you look at the data structures within class, you will actually find this completion of Clark of these days. Then in logic programming, of course, negation as failure was the big thingy. And again, now actually my just a sec, I have to charge my pen again at the same time, because since I was not prepared to give it on the iPad. Okay, so then, of course, negation as failure, that more or less you can derive a negative literal by a finitely terminating failure of a derivation, right? That was more or less what was happening there. And then, of course, the non-monotonic reasoning, where really different semantic approaches to handling negation or defaults also come up. Autoepistemic logic by Moore, right, where the idea was, I do a self-reflection about my knowledge. The idea is, well, I don't have an elder brother, because if I had one, I would know it. That was a bit the idea, how to do closed world reasoning. Or default logics by Reiter, where you explicitly add additional inference rules. Circumscription by McCarthy, where the idea is that you have certain predicates which denote abnormalities and you want to minimize them. So you reason with respect to minimal models, right? But this was all very, well, as I said, I think at the time people may have called it esoteric as well, but you really had to capture a phenomenon, and very different mathematical tools more or less were applied. Of course, in non-monotonic reasoning, the real difficulty came from the fact that people wanted to use first order logic and do non-monotonic reasoning with first order logic. Well, and you can imagine that everything that really happened on first order got undecidable. Okay, then amalgamation computation. Well, the interesting thing is, at some point, all this zoo more or less collapsed. And what is interesting is that actually it were the semantics from non-monotonic reasoning that led to the canonical ways of logic programming semantics. So actually, stable model semantics as such was the definition of stable semantics as such was first published by two French women, Christine Froidevaux and Nicole Bidois. And they actually derived the semantics of stable model semantics from default logic, while Vladimir Lifshitz and Michael Gelfond published their paper later. But of course, they're very reactive, and they are more or less looked at the fathers of stable model semantics. But historically, if one just looks at the date, it's actually two French women who actually derived it from autoepistemic reasoning. And what is, I think, more astonishing, Vladimir told me the other day that at the same time, there was in philosophy, they also proposed it, but I forgot the name, unfortunately, but there's yet another completely independent proposal of the same semantics at the time. And so more or less what well-founded, because I mainly talked about stable model and well-founded semantics, is the relation is very nicely described in the second bullet, where if you think of computation, you compute the stable models by propagating through well-founded semantics, because well-founded semantics is propositional, and then you branch. This is actually the original title of a paper by V.S. Subramanian at the time, who described that. Okay, so more or less, then again, we had this big zoo of different semantics, and they all more or less converged to well-founded stable model semantics, where well-founded was more or less the propagation, the characterization of the propagation strengths of a solver. Well, application. Well, I've shown you some applications on the last slide, so there's not so much to be said about now. But what I find so interesting is the rediscovery of what actually the logical foundations are. Because keep in mind, everything that happened up here, everything that happened up here, you took more or less classical logic, propositional first order, and you did something with it. Right, fixed point constructions, reducts, or whatever. But it was actually in the 90s that David Pearce discovered that logics that were studied by Heiting and Gödel. So Heiting's logic is the logic of here and there. This is actually this is a Kripke structure with two worlds, which is an intermediate logic. So it contains the tautologies of intuitionistic logic, and is more or less the strongest intermediate logic. So once you add something, you get to classical logic. This can be seen as the monotonic foundations of this. And at the same time, this logic is equivalent to the logic G3 of Gödel. And when you do minimization on both of these monotonic logics, you exactly end up with stable model semantics. And actually, once this was discovered, and I have to admit, it also took me a couple of years to really realize how important this was. You can now very easily design new knowledge representation languages by combining logics. So what we, for instance, do now, we have a version of our solver that treats linear temporal operators and dynamic logic operators. And you can very nicely build this up from first principles. You put the logic, you put it together, then you delineate the logic programming fragment, and then you have a semantics and you can think about application, implementation of it. So anyway, as I said, I have some slides on that afterwards if you're really interested, because this is one thing that keeps fascinating with me since a couple of years. And then, yeah, as I said, integration is now the big thingy because you want to put this in practice. Yeah. Okay, foundations. So now I do something that I hope you it's not too oversimplified, but I can go through this a bit more quicker. Now let's look at actually at some semantic issue, what this all means. So this is more or less a logic programming rule. You have a head, and A, B, and C are atoms, and we have here the negation in the body, and the comma here is a conjunction, and yeah, that's it. And one way to view a set of such rules is like a normal form, like a conjunctive normal form. Because spoiler ahead, right? So for instance, the decision problem on such programs here is NP complete. But actually, if you have an arbitrarily nested propositional formula and you want to determine the stable model, this goes to the second level of the polynomial hierarchy. Okay, now let's get a feeling for that. So the semantics is then given by associating stable models with a program. And these are actually classical models, where this is, of course, in quotes here, where each atom that is true in such a stable model must be justified. And justification means more or less there is a sequence of rules where more or less you apply forward chaining, modus ponens, right? Where you took actually the implication in a literal way. And actually in the logics I was describing before, implication is a primitive connective. And then you derive more, everything that is true in a model must have a derivation from the fact via implications. Okay, let's look a little bit more into that. So I'm simplifying this here, and this works for normal logic programs, but not in general. So just keep this in mind. So I think everything we all know from our undergraduate days is truth tabling. This is more or less, if we now want to look at propositional logic, and I just use now SAT as a synonym for propositional logic under classical semantics. We have here our interpretation, and we want to evaluate the formula to determine which of the interpretations are the model. So what we do is we take the truth values that we have on the left-hand side, we copy them in here, and then we apply more or less the logical rules to simplify that, right? So we evaluate negation, we evaluate implication, we then simplify it accordingly. Then this goes on, here are the ones that are true, and we do this until we have finally completely evaluated the formula, and wherever the formula was evaluated to true, these four guys here, these are the models. Okay, but actually what we don't do, we guess more. Well, actually here there is no guess because we go through all the interpretations. But whenever we have such an interpretation here, we never ask ourselves, oh, is there any reason why B and C are true? After all, this is just an assumption. You start with assumptions, and then you look actually how things work out. Okay, I'm saying this, of course, in that way because in ASP the idea is to do this a bit differently. So yeah, so I forgot this. So of course I'm using here a lot these set notations here for models. So these four guys here I will just denote by the set of the entailed atoms. So let's do the same thing in ASP now, truth table. So what you do is also you put actually the truth values of the atoms into the formula, but only whenever something is preceded by a negation. So that's what we get. So we see here B is the only subformula preceded explicitly by a negation. And again, this now works nicely with the normal logic programs. One has to do a bit more effort in the general case. So only B is replaced. And then you just evaluate. You more or less simplify until you actually end up with what is called the reduct. And this is these are just definite clauses or clauses that do not contain any negation anymore. Okay, now now that we have this reduct, the idea is actually to take this and to see whether our assumption that we did, that B is true and C is true, can be justified. Is there a proof for that? And that's more or less then. So we look at the four models, and so here actually we, of course, since we have definite clauses, there's always a smallest model, and we just have to look into this guy. So here, from this guy, no atom. We cannot derive any atom. I'm just looking at atoms now. So we cannot derive A, B, C. So, but here we can derive A, and here as well. But it turns out that, for instance, here C cannot be derived. And then we can check actually whether whenever we assume that something was true, can we actually reproduce this via a proof? And this is now given here in red. So whenever there's something in red, we will not get a proof in that way. So we assumed a proposition to be true, but in the end, we cannot prove it, at least if we understand a proof as a derivation from facts over implications, right? The only model actually where we can find a proof for all the atoms we assume to be true is this one. And this is actually, and we can do the same thing for all the interpretation, but there's nothing to specify. This is actually here the only stable model. And this is actually what happens when in the original definition of Gelfand and Lifshitz, right? You more or less do a similar thing that you do in classical logic with truth tables. It's just that you stop at positive format and you use this reduct to check actually whether you can really prove something that you only assume to be true. Okay, so we get only one stable model here, which contains A. Good. Yeah, so in a way, the stable models are the smallest models, and there's always a unique smallest model of each reduct in the case of normal logic programs. So this was more or less in a very simple way to describe the original reduct. There is actually a paper by Vladimir Lifshitz which keeps changing its titles. I think now the title is 13 definitions of stable model semantics. It may meanwhile be more than that. And he started out with much less. But here's the relation perhaps nailed down. So if you use ASP and you want to get SAT out of it. So again, SAT stands just for a propositional logic on the classical semantics. You simply add the laws of the excluded middle, that is for each proposition an A or not A to it. Because this is exactly the axiom that goes from this intermediate logic into classical logic that takes you there. So this is more or less what you have to do. If you want to encode SAT in ASP, you write things down as an ASP specification and you add the laws of the excluded middle. And actually the syntax of this in the program is, so if you want to express A or not A, this is expressed as a choice rule, which is just a set like this. On the other hand, if you want to encode ASP in SAT, you have to do some heavy lifting. So you have to add what is called completion and loop formulas. Now, completion formulas are actually what Clark invented. It's more or less the program gives you the sufficient condition, and you add the necessary condition. You turn implications into equivalence. But this does not forbid infinite proofs. Like if you have a program P if P, if you do the completion of this, you turn the if into an if and only if. So you have P if and only if P, but there's still somehow this infinite derivation which is still there, and you get two models of this. And this is why you need loop formulas. And these guys are bad in the way that these loop formulas, again, you look at the dependency graph and you look at all the strongly connected components, and there may be in the end an exponential number because there's no minimality criterion on them. So there may be an exponential number of loop formulas. This actually means that if you translate ASP into SAT over the same language, so without doing a Zeiten translation, without auxiliary atoms, so over the same language, you risk an exponential blowup because you may have to add exponentially many loop formulas. While if you encode SAT in ASP, well, this is just, you just add the excluded middle, there's no, it's a constant overhead, right? So this is actually one thing, and now you may ask, oh, this gets more complex? Well, of course, both decision problems, at least for program rules and CNF are in the same class. So there is, of course, a translation with auxiliary atoms. But you may ask, where does this show? And in fact, it shows, and I'll give you an example later on, because things like, of course, defaults can be very trivially encoded because it's non-monotonic, but also reachability. Reachability can be just encoded in a standard way. We'll see this in a second. Okay, good. So this was all about ASP viewed as normal logic programs, but keep in mind, if you want to check a propositional formula, then you really go one level higher. this is the price that you have to pay for closed world reason. But what is nice again, yes?
Can you say anything about like this when you evaluated your formula? What was the reason for only substituting values for negated axioms and then propagating? Like how I didn't get it. I guess what's happening.
My suggestion. This is actually the definition of a stable model is so you do a reduct. You have a program. You do a reduct with your guess, and then you calculate the smallest model of this, and this is. And if the original guess, if you solve this fixed, this is more or less the criterion, right? This was more or less translating this into truth tables. So my suggestion is.
And the guess, just to clarify, the guess are like you care about the atoms we set to true. Those are the ones.
Yes. But my suggestion is, let's postpone this question, and I can show you actually this logic of here and there in the end, because this is actually interesting to look at.
Okay.
Good. So here we are now. Let's actually see what you can do with ASP, right? Again, this is not very deep, but at least we cover a lot of ground in that way, and that is more or less my intention. So this is more or less the workflow that you have in ASP. So of course, what you want to do is you want to go from a problem to a solution, but the first thing is you model your problem. And again, this program thing is a misnomer because there is no program. There is a specification, and the order doesn't matter and all that type of thing. So you model your problem, and then this is a first order specification with this first order variable and so on and so forth. Then you have here a system that is called grounder, and this grounder is replacing all first order variables in a systematic way with the elements of the Herbert universe. This grounder already takes the semantics into account. So for instance, if there is a rule, if you have an atom, that does not occur in any head, in any conclusion of a consequent of a rule, you can set this atom to false because it will never be derivable. And such things can be done in a cascading way, and this helps. But of course, in the worst case, actually grounders are, and now this is a bit of a funny fact, grounders have function symbols and hence they are Turing complete. So you can encode Turing machines in just this grounding step. Okay, so what you then get here at that point is a propositional representation of your program. And actually here, the internal format, you can think of this as Dimex, just a richer format, right? And then you have the solver, and this solver spits out the stable models, but actually it can do more things, right? On top of the stable model. And of course you interpret this. Okay, so yeah, so I could have done this a bit more animated, but yeah, sorry for that. I was still a bit with the last question. So once you have done that, actually one thing that is particularly nice I find about ASP is because once you see your stable model and you see, there's a bug or there's something that is not right, it's a very short distance to elaborate this and to go back to the specification. Because again, talking about SAT, right? So what more or less you do in SAT is you have to write a program that takes the problem and maps it here. So it's not that you have a modeling language. It's not that you have a general purpose grounder for things. And that's, of course, the nice thing, because you just get from your stable models, you can go back to the modeling language, modify your representation, and you don't have to delve in to the code of a Python program or C program or whatever that produces the Dimex format for you. You know, it's one thing that you have written this thing, but if someone else has written this and you have to go in, so it's not really what we call elaboration tolerant. That's actually I think one of the unique selling points of ASP, that there is a modeling language and a general purpose grounder to translate this into a propositional format. And keep in mind, again, I think if you really found the super encoding and that's the one, well, why not do this effectively? Because of course this is a general purpose thing. If you know exactly that this is the very best encoding, of course do that. But for teaching, for elaborating, actually I mentioned before the encoding for Debian and Ubuntu software configuration that we did. We did a lot of modeling effort, but at the end we had, I think, almost a dozen different encodings, and we couldn't tell them apart. So we had to run benchmarks and change them, do things, right? And doing this on a high level is so much more effective and than doing this in an imperative programming. That's one of the big differences. And again, you can write set formulas just by writing the ASP code and adding the excluded middle, the choice rule. Then you have then you have propositional logic semantics. There's actually nothing to be lost there. You just have more convenience. Okay, here are the language constructs. So first of all, you have a logical format. You have predicate symbols and objects. Everything is terminated by a dot. And then you have first order rules here, where everything with an uppercase letter is regarded as a variable. This is then negation here. And then, of course, what happens is these variables are instantiated by the constants. Here we only have 42, so this gets replaced by the grounder. So what else is there? So first of all, what is very handy when modeling are conditional literals. Logically, you can view them as a nested implication, but actually what they do is, this is the body. So the connector here is a conjunction. So you will get the conjunction of all Q of X whenever there is an R of X. So for instance, if you have facts R of 1, R of 2, R of 3, then afterwards this rule will be expanded to P if Q of 1 and Q of 2 and Q of 3. That's a type of quantification. So if you do not know actually which objects will satisfy R, but you want to collect all of them and in form of Q or so, then you can write this at the modeling phase without giving the full instance or thinking about that. That's actually comes in pretty handy. One way to that's what I forgot. One way to view this is, and you all know that, is you can think about this as a set, right? And then this is actually the set of all Q of X such that R of X holds. Just that here, once you compute from this intentional description, the extensional description, it is put into a conjunction. That's more or less the feature of this. Oops, I'm sorry. That's the feature of this modeling construct. And again, it comes in very handy when you are a bit more experienced.
And Q of X and R of X, we should think of them as like first order logic, like predicates.
Yes, exactly.
And P of X are different. Like
yes,
you have a P of X.
Yes, actually, you are allowed to have. So a predicate is a symbol associated with an arity. So the predicate P with arity 0 is different from the predicate P with arity 1. Okay, so this guy and this guy are different.
Okay.
Implicitly, yeah.
Mm-hmm.
Implicitly, all these rules are all quantified. And of course, there can be more variables. But keep in mind, we are. So we may have an infinite Herbert universe, but the grounding only terminates if it is able to find a finite grounding, right? And this can be either be achieved by modeling, or actually that the grounder has some techniques to find finite representation of infinite ones. Because let me come back to that at the end of the slide. Actually, that's actually an interesting point, because we have to the semantics of. So, for instance, what is the semantics of the grounder? What does it do? What is because in the end, if you input, as I said, the guy is Turing complete, and if you have function symbols, let it be integers or real function symbols, you end up with situations actually that you create infinite objects, and the semantics actually of the grounder is described by an infinitary logic. And I can show you this now in a sec with the constructs. But we first have to. I'll stack this and I'll pop the stack once I'm through with it. Another connective is disjunction. So in the same way as in the, again, think of it as a normal form, right? as in the body, you have the conjunction as the primary conjunctive, and the head you have the disjunction. This is a semicolon. However, this disjunction here is neither inclusive nor exclusive. It is minimized, and this is actually so when you now not have normal logic programs, when you allow this, then you jump also to the second level of the polynomial hierarchy due to the minimization on the disjunction. Okay, a very popular construct in modeling are integrity constraints, and we will see them afterwards again. This more or less can be seen as an implication that entails falsum, right? Which says it must not be the case that there is an X for which Q of X and P of X hold. People, when they see this the first time, have a bit of a problem, because if you want to say that something has to hold, you have to formulate this in a negative way, but you get used to it. Then here, choice. You want to make choices. So you want to say, okay, if I pick a Y for which R holds, and then I look at all the X's for which Q holds, and then I get a set of instances of P of X, Y. I have to make at least 2 and at most 7 of them true. Cardinality constraint. Same thing works with aggregates, right? You can then write this a bit differently. Actually, this is more or less a shortcut, but here you can have a sum constraint, and you can then here collect terms, and for all the integers that you collect here, you will take the sum, and the sum should also be between 2 and 7. Okay, now here's the point where we can talk about infinite expressions. Because if you have function symbols or whatever, right, then it may well be that here this set, or also this set here, is infinite. And then the question is, can one find a finite representation of it? Sometimes it doesn't, one can't. But the grounder normally is pretty good at analyzing this and finding out actually whether there is a finite representation. And again, what helps a lot here in the evaluation is closed world reasoning, having the semantics in mind. Because if you know, let's say here the X ranges over all integers. But if you know that in your program you can only derive Q of X for 1, 2, and 3, and the others are not derivable, then you can imply a simplification saying, well, even though in principle my Herbert universe contains an infinite number of instances here, my semantics says that I can't derive them, hence I can simplify them away. Then you can reduce an infinite expression to a finite one. So just to because I think this is an interesting theoretical thing to look at. Okay, then this is more or less these are the basic language constructs. Then there's also optimization. So there are 2 ways to express actually multi-objective optimization. One is simply to use something like integrity constraints, just that you weaken this by replacing the minus here through a tilde, which is a weak constraint, which says, well, if Q of X and P of X C holds, then this gives you a penalty of C. And then you can also add somehow something like a level, because there's the multi-objective optimization here works in a lexicographic way, right? And more or less, the higher the level, the higher the priority of it is. And again, now I have to charge my stick. And these are weak. You can express in this way weak constraints, and you can have several of them. And in the same way, you can bundle them together in one objective function and write just minimize. And this is more or less the same. The expression, the weak constraint above is roughly equivalent to the minimize statement below, right? So this and this are 2. Unfortunately, yeah. Once my stick is loaded again, I'll come back to that. Good. So, but keep in mind, these are meta statements, right? Because they talk about the program, right? While from facts to aggregates, these are really the object in the language. Okay, so let's look at an example. Traveling salesperson. Why am I choosing that? Because it has these 2 features. First of all, reachability and optimization in one example. So this is more or less the problem instance. You can write down a problem. You say the start node is A, and then you have 4 cities, A to D, and you have roads among them, and they are annotated with a weight which stands for the distance. Okay, now let's look at the encoding of this. So the first the first rule says, actually, whenever I have a road, I can decide to travel on this or not. Keep in mind, such a choice, right? So opening brace, closing brace stands for law of the excluded middle. Either I make this true or I make this false. I treat this then more or less as in classical logic. I can choose true or false. This actually gives me now my solution candidate. That's a bit the idea, right? This very first rule, from a methodological point of view, this is your generator, right? There you generate all types of solution candidates, and then you test it in the rest. So the two next predicates visited. Let's see how good my stick is now. Yeah, it works again. So this more or less it analyzes what the guess that we have done here, and it checks what can we actually visit from our guess starting at the start node, right? So we start at X and we guessed that we travel from X to Y, then Y is visited. That's more or less the base case. And here's the recursive case. So if we have shown that X is visited and we decided to travel from X to Y, then Y is visited too. Now we've analyzed our guess, and now we want to make sure that there is no city that has not been visited, because this means more or less that we really went to all the cities, right? So we analyze the guess, and then in the end we make sure that no city is visited twice. So we look at all the outgoing, for each city we look at all the outgoing edges, and we want to make sure that it's not the case, again, that's an integrity constraint, that it's not the case that there are two or more outgoing edges. And the last one is not needed, but it's actually pretty effective. It's just the same thing for the ingoing edges. And that's the traveling that's not the traveling, that's the Hamiltonian cycle problem. And now to turn this into a traveling salesperson, we add the objective function. And here I used a weak constraint, which says I pay a penalty whenever I travel on road XY, I pay a penalty of D. So this then adds optimization to it, and this way I can describe the traveling salesperson problem. So yeah, I think this is nice because it's first of all, keep in mind that whenever we want variables to be flexible on their truth value, to be free to select the truth value, we have to allow that. Because otherwise, closed world assumption kicks in, and if you leave things undefined, they are set to false. This is different from propositional logic, right? So this is what we do here, where we use, again, this is the law of the excluded middle for all these guys, where we say, if for each road, you can decide or not to travel on it, and this is more or less gives you all the possibilities. So the guess is then restricted, in this case, to this guy here. And then from a methodological point of view, this is the guesser, this is the checker, and this is, if you like, the optimizer or whatever. And that's, of course, the instance. That's how you write down ASP programs. And yeah, and keep in mind, so what you writing a CNF is really trivial. You take all the variables, you put them into as choices, logs the excluded middle, and then your clauses in CNF you just put here as integrity constraints, and you have written down your CNF, and which is treated under classical propositional semantics. Good. So yeah, so now if I put this in as good practice here as well, you have an instance file and you have an encoding file, and the encoding should of course work for all the instances. Now, if you launch this, I now here call Klingo, and Klingo is the combination of Gringo, the grounder, and Clasp, the solver. And this will do the grounding and the solving at the same time. And so what you see here, you get a first, actually, why don't I do this here with red? So you get a first answer here. And this is, here are the atoms of this answer, because of course you have symbols and that's why they output. I omitted some of the guys here. And this has an objective value of 100. Then this is just branch and bound optimization. It tries to find a strictly better one. So this constraint is added and it finds one. This is then the second answer here. These are and this is the better one. And then again, it tries to find a better one, but that fails. And hence we know that the last model was the best one. Actually, the default option is branch and bound, but Clasp also does unsatisfiable core-based optimization and combinations and so on and so forth. Good. So, so the other thing I wanted to mention is in ASP, again, it's about knowledge representation and reasoning. So it's not just about satisfiability testing. You also want to do you want to enumerate models. One thing that actually was pretty clear to us from our, again, from the KR perspective is you wanted to have projective enumeration. So you wanted to enumerate the models, but only relative to a part of the alphabet, and also then of course avoid redundancies in that. And actually, I think Class was one of the first solvers who had a CDNL algorithm tuned to enumerative projection, and which actually worked without solution recording. Not to say that solution recording is sometimes pretty good, but it has this option. Then one thing that is also very nice, which we like a lot to approximate our answers, you can compute the intersection and the union of the models. That's also one functionality. And of course, you can do optimization and combinations of them. So it's in bioinformatics, actually our biological persons were always a bit stunned when you describe the biological organism, then you get, I don't know, 100,000 models. Well, which one is now the real one, they ask. At least here with the intersection and the union, we can say, well, what is true in all the optimal models, right? Or what is not true in the union of all the one. And this way you can at least give an upper and a lower bound of things that must be true or must be false. Good, so this is the architecture of Class. Class is multi-threaded. You can go up to 64 cores if you like, but I would not recommend this. So let me just briefly go a little bit through this. So you start with a logic program, and then you have two phases of pre-processing. The first one is actually on the logic program. So you more or less do simplifications, knowing that you have a logic program in your hands, and then on the closed world reasoning. Then you translate actually the logic program into what we call no-goods, but you can see this as clauses, right? And there you apply also pre-processing that is inspired from techniques in SAT, but normally you cannot apply a single technique just off the shelf simply because of closed world reasoning. You have to think this through and modify it, and you have to keep more information around because also for the proofs, right? Then actually what you have in Class, and this may be a bit old-fashioned, but for ASP problems, it is really nice because ASP problems consist, let's say, over a rule of thumb, 70–80% of binary clauses. And there are also some ternary ones. That's actually why we have special data structure as one of the first SAT solvers for short clauses, for binary and ternary clauses. And they are also shared among all the threads. Then, more or less, you can see actually a solver as pretty much following the basic CDCL algorithm. Just of course that you have to have actually we implemented as propagators that account for these additional formulas, in particular for the loop formulas, because you cannot compile them out because this will give you an exponential blow up. So you have to have a lazy propagator that spits them out if needed. So one way to look actually at an ASP solver here at this level here is like an SMT solver. So more or less you have a SAT solver, and the theory is ASP specific. One way to do that. Another thing that is very typical is this enumerator thingy. That's actually for the reasoning modes, because this is the guy that always tells the solver, if he found a model, what to do next. So for instance, if you are optimizing, this enumerator will know, oh, I'm optimizing. So thanks for the model. Here's a new constraint. So the one that you have to find a better model now. And then the solver goes on and so on and so forth, right? Okay, so this is a very rough overview over this. But again, keep in mind what I was saying at the beginning. Benjamin keeps saying that 10% of Clasp's code would give you a SAT solver. So there's much more you have to do in order to make it an ASP solver. Yes, and okay, so I'm almost at the end. Let me talk about omissions. What didn't I talk about? What I find interesting. One thing that I really like is metaprogramming. And since you have a syntax, what you can do is you can actually describe your own ASP solver as an ASP program, and then do modifications to it, right? So this is, again, I don't know, for each language construct, you have a rule. And then if you want to reinterpret one of the constructs, you just write this in ASP. You can do metaprogramming that way. You can also then compute other things, and so on and so forth. Qualitative and quantitative optimization I already talked about, right? So you can also have qualitative preference and combine them with quantitative preference and have arbitrarily nested expressions that then actually are then taken into account when optimizing. So then this one actually I also like a lot. This was actually inspired by work of Jussi Rintam. You may remember Jussi for a time was working very strongly on SAT planning, and he tried to look into the planning techniques and integrate them into a SAT solver. And I thought this is a great idea. It's just in ASP. The idea is that you do not integrate this, hardwire this in the solver. You put it out to the user so that he can actually have, that there are language statements that then actually provoke this action. And heuristic programming comes from that. So what you can actually do is you can write almost like a rule where you say, oh, this atom here, this is like in the head of the rule, will be biased when you do visits or when you do Berkman or whatever by an additive or a multiplicative factor, or you have layers to choose from. And actually, for planning, for planning, when there is a plan, this allows you to speed planning up by orders of magnitude. I think in the paper we reported two orders of magnitude. Of course, when the thing is unsatisfiable, these heuristics are not so nice. Or when you want to do optimization. So a very robust way to boost the convergence to an optimum is by, when you have a minimize statement, to work on the sign heuristic to say, look, these atoms that are in the minimize statement, preferably assign them the value false, or preferably assign them first, right? And these are, again, just in case where whenever the choice is made in the solver, these things are looked at. There's no propagation, nothing else happening, and that's actually a pretty nice thing because you give it to the user. You can write it down. You can specify it in his encoding on a first order level. Okay, then the last two thingies I think it's more as engineering. Theory solving is, of course, that if you want to include foreign theories and augment the inference in the solver, just like SAT modulo theories. Multi-shot solving is a bit like incremental solving, but it's, I would say, a bit broader, where the idea is what multi-shot solving gives you, you can launch solver objects and then talk to them, right? You can add information, retract information, change the configuration of the solver on the fly, or get a model, analyze it, feed something back. So more or less, the solver is an object with which you can interact. And what we were doing recently, we were actually augmenting ASP with linear temporal and dynamic reasoning, actually to tackle temporal problems. One thing I didn't talk about, we also have notably here in the theory solving part. Of course, the first integrations that we also did when pairing ASP was with constraint processing systems. Like we used G-code at the time, right? But then you look at your system, and after a while you say, oh, it's great, but it's a bit ad hoc, right? Because what you do is you have this non-monotonic reasoner, this closed word reasoner ASP, which really, where the semantics has something to say. And then you plug in a reasoner that is monotonic. So immediately you had the dilemma. If you have, how do you assign a default to a constraint variable? Well, you can't, because either you model the variable in ASP. This means, you can assign a default value, but how will you handle integer values? Well, grounding will kill you. Well, if you then model it as a constraint variable, great, you can handle the integer domain, but you cannot handle you cannot model it as a default, right? Because you just plug together two systems, and it was nice, but it was not really semantically coherent. And actually what we are doing now, we are looking at semantics for such systems that actually allow you to cover the whole combination under one semantics, and also actually then have arbitrary theory solvers, and then give them a non-monotonic semantics, for instance. And we do this with denotational semantics because, of course, we want to stay general enough that we don't have to talk about specific theories. And we have this implemented, which I found pretty cool. Actually, sorry, I'm bubbling, but in our company, actually, the solver that we use most is actually an extension of Klingo with difference constraints. This works like a charm and covers so many applications out there. Okay, anyway, if you feel playful, just just visit our GitHub site, which has just the name Potasco. And there you can find, I think, over 100 implementations and systems, drafts, and so on. You can just have fun with them. Good, then let me recap the take-home messages. So first of all, ASP is a modeling, grounding, and solving paradigm. And actually, if you look, for instance, at our papers on extending it with modulo theories, it's not enough that you use an SMT solver. No. Solving is not enough. You have to think about grounding. You have to think about modeling. Actually, what Klingo gives you is a grammar formalism in which you can then actually write a grammar to describe the new language elements. And then the grounder will respect, you can model them with this, and the grounder will respect it and give it to the solver. And of course, from a technological point of view, ASP is a combination of deductive database techniques, logic programming, knowledge representation, reasoning, and SAT as a representative of CDCL. And if one is very exact, one can actually look at this as an SMT search procedure where you have several theories. For instance, you have the theory, of course, that gives you the semantics of ASP, closed world reasoning, and optimization. This would already make two of them. Good, and again, if you are interested more in that, we have this site potasco.org. So Potasco stands for the Potasco Answer Set Solving Collection, and now actually, unfortunately, now my stick left me. There is this teaching.potasco.org gives you a full-fledged master course on ASP with videos, Jupyter notebooks, and all this type of things. So this is one of the positive Corona effects. And now to wrap up. Yeah, and it's fun, of course. To wrap up, after all, it's all about Tweety, and this was actually an idea that came to me when I gave an invited talk at the SAT conference at Bordeaux at the time. So this was actually, I don't know whether you remember these readings that were in AI at the end of the 80s, beginning of the 90s, and of course this was sitting on my desk. All the readings in normal scientific reasoning. How can you more or less equip this little penguin so that it flies? And then I think thanks to SAT technology, we now have this little guy here. Well, where we more or less equipped now Tweety with rocket engines, but taming the guy is still something. Okay, good. So this ends actually my talk. And actually, I don't know how was I. Oh, not so bad. Perhaps a bit longer than I thought. So should I stop sharing now, or?
I'm thinking that maybe people, there might be, so we'll open up for questions. Maybe keep the sharing in case people want to ask about the slides. I certainly have a few questions. So if you're doing multi-objective optimization, so this is probably a very basic question. Like, but what is it that you get back? Like, what does a solution look like? Or do you get a bunch of solutions that is somehow describing, some kind of, what's it called, Pareto frontier, or like what do you get?
Well, the built-in multi-objective optimization replaces the multi-by-lexicographic optimization. So you can have several objective functions that are ordered by a priority level, by priority levels, right? And so what you then get is in this case is when it runs through is the model that is is one model or all models depending on what you want, that is optimal with respect to this lexicographic ordering of objective functions. If you use the aspirin system that we developed, where you can actually use Pareto and all that type of thingy, you will get several ones. Or actually, you will get I think it's the same thing. If you just ask for one, you get one Pareto optimal. If you want all, you get all of them, which is hard enough. Or if you want 5, you get 5 or whatever. So in an ASP solver, you always, if you say nothing, you also only get one model. But if you give it a 0, you get all, and if you otherwise give a number, you get the number you want.
Okay. Then I was wondering, what's the? As I understand it, it seems like you can extend ASP, you can sort of, I mean, it seemed like you can sort of do SMT, but based on ASP rather than somehow Boolean satisfiability. And it seemed that you extended it all. So it's kind of a base language that you can extend in many different directions, was the impression I got. So what then is like what's like the killer reason why I would want to use ASP rather than, you know, starting with, say, SAT or starting with mixed integer linear programming? Or
again, if it's just on the ASP, SAT, or MILP, I think it's really the modeling language and the grounder that comes with it. That you get very quickly. The thing is, a typical example is when we either work with other academics or with a company on something, they bring a toy example, we sit together, normally in the lab, right? Then we discuss it. And normally the idea, well, I asked them before, bring a toy example that of your application that we can resolve with paper and pencil. And after 1 or 2 hours, we have this modeled. And then that's also a stereotypical thing that always happens. Then we push, then the guys are very excited about this. We push the button. And well, what always happens is they say, "Oh no, but that's wrong." And then, well, silence. And then I ask, "Oh, what's wrong?" And they explained and said, "Well, you didn't tell us about that. Let's just add these constraints." And then you do this a couple of times, and then more or less they go out with the first model of their application, right? And I think this nicely shows actually what the benefit of this modeling language. Rapid prototyping, really transparency, and I think this is really what makes it different. What makes a difference.
So rather than like you're saying that if I write my problem as a CNF formula, then it's very hard to know what I've written, or even like an integer linear programming is not clear, but somehow it's more intuitive. So it's easier to parse, like to make the mapping from reality to.
Well, there are two things. One thing is. One thing is you as far as I know, right, there may be things now around, there is no modeling language for SAT problems. There are some, I know, there was the guys at MIT for software engineering or whatever, but the thing is, and Valentin, so anyway, so you do not want to sit down and write your problem in Dymex. That's the provocative answer. Right?
No, it's a perfectly fair answer.
Yeah, and ASP actually allows you to actually, if you want to, don't even take Clasp as the solver, right? But you can write it in ASP's modeling language, declare all the variables as choices, and then you let yourself output Dymex and give it to a SAT solver. But then you can start modeling on a higher level. Right. So I'm not saying that writing down necessarily rules is definitely what you absolutely want. I find it intuitive, but I grew up with it. So, but at least having this modeling language is a big asset.
I see. And then, but then on the other, you could say, okay, if we're doing some kind of first order-ish logic anyway, then why not do first order logic and, I don't know, run Vampire or whatever. But then maybe like the point is with ASP, you have somehow a nice enough subset that you get better performance or better efficiency.
Well, the thing is, I think this question has been answered by the SAT community, right? Because I think until, I don't know, I happened to be at the ECHI where Bart and Henry presented their paper on solving planning problems with SAT, right? That was big breakthrough. And until then, the world was dominated by theory improvers. But then actually, my impression is that theory improving is almost non-existing. And SAT solving is the basic technology when it comes to solving logical application problems. And this is, this play between first order and logic and SAT, right? They already sorted that out. So ASP actually, what ASP adds is because at the end of the day, it's a propositional solving approach, right? It relies on the same benefits that SAT solving technology relies on. Because if you would go back to unification and all that, I think you would lose a lot of speed. And I don't think there's any anything to be gained to suddenly look at a first order ASP theorem program. That's a bit of a nuisance that I can't see your faces now.
Yeah. So I don't see if there's one comment in the chat that I'm debating with myself whether I will be able to read it out or whether I should just ask Mate to speak. I don't know. We can try. Mate, do you want to say your comment or do you want me to read it for you? You should be able to speak now.
Yes.
Yeah.
Hi. Yeah, no, I just wanted to note that I guess some people are using/abusing the SMT-lib quantifier-free bit vector logic as a sort of a modeling language. I'm not saying it's great. I'm just saying that that does happen, and I've seen people using Z3, for example, to do that, and then ask Z3 to output an SMT-lib via Python, and then like grind that down with like say STP into a CNF, and then eat that. I mean, it's not great because you don't know the exact mapping once all this grinding has happened. I think, and there are some other specific modeling languages like ENF, which is specific to a field, like in that case, cryptography. And there are a few now, in SageMath, for example, has an ENF to CNF converter. I mean, I'm not saying this is great. It doesn't even touch, what you have done in terms of complexity, being able to debug. I know that your system also has that, but I just wanted to say that there are some sort of attempts, but I don't think it's as comprehensive and as sort of well done and integrated as what you have presented here.
Well, thank you, Bate.
And Kieran McCreesh also had the comment that in constraint programming, there's a mini-zinc that can be turned into CNF, but not necessarily in a good way. But I guess, so the point is that somehow if you're doing SAT solving, I think it's clear that there is some layer. I mean, you're not writing your problem in Dymex, right? You're writing your problem somewhere else, and then there's a Dymex generator somehow. Probably, right? So I have one more question. I don't see any other questions, so I guess I'll ask it. So what about correctness? Or if I want to certify that the answer of class for Klingo is correct or optimal, or like what the SAT community would call proof logging?
Actually, there was some work to do this for ASP as well by Johannes Fichte and Markus Hescher, but it's not something that has found it more in the mainstream. There are a couple of things. For instance, I'm now shifting a bit the attention because there I can better explain it, right? Where it's really hard to follow certain functionalities. For instance, if you want to count models, so one can do this, for instance, for a very simple fragment, like just normal roots. But once you have all the aggregates and this language content, it gets really difficult, and you really have to put a lot of effort into that. And I think for the proof, this is more or less the same thing, right? As long as you just stay with normal rules, that should all be fine. But once you have these other language constructs, it's not obvious how you do that, and hence all these things are not really getting addressed because in our community there is a much smaller percentage of people doing implementation than compared to the SAT community.
I see. I note that Johannes and Markus, I think, are both among the attendees. I don't know if you want to comment on the proof logging aspects, or otherwise, I think I don't see any other questions.
Good. And I can stop sharing.
So I'll just, on behalf of all the listeners, I'd like to thank you for a great talk, very interesting.
Thank you.
And and for pointing us to resources where we can learn more about ASP.
Yeah, as I said, at potasco.org you find a lot of resources and you can check it out.
And Kuldeep is reminding us, okay, do I have the link somewhere? Do you have the link somewhere, Kuldeep? There's a, for people attending the workshop, there's a GatherTown link if people want to hang out, which is now being posted in the chat. So please do feel free to join there. And next Tuesday, we're having another overview-ish tutorial-ish talk, which will be on maximum satisfiability or max sat solving. So I'm looking forward to seeing you then, but this is all for today. Thank you so much.
Okay, thank you. Bye-bye.